are two kinds of equilibrium, that is mainly physical equilibrium and chemical equilibrium. It will not reach the equilibrium because they are reversible in nature. It can reverse at the end of reaction or in the mid of the reaction also it can be reversed. The collision between molecules which are present in liquid phase as well as in the vapor phase, it starts get colliding. Their pressure will exert, that pressure will call it as vapor pressure of the liquid. Everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today we are starting up a new lesson, that is from Unit 7 Chemical Equilibrium. First we will see the exam corner. The number of periods required to complete this chapter is 20 periods. The marks allotted for this chapter is 11 mark. In this session we are discussing some of the introduction points regarding chemical equilibrium. In that types physical equilibrium and chemical equilibrium will discuss. Introduction. The state at which the concentration of reactants and products do not change with time is known as state of a chemical equilibrium. We know that while proceeding the reaction we will tell that it has to reach some equilibrium point. That means the state at which the concentration, any reactant has been used to form a product, after formation of product, it will reach the equilibrium point. But the concentration of reactant and the concentration of product will not changes with time. The state at which the concentration of reactants and products do not change with time is known as a state of a chemical equilibrium. Most of the chemical reactions do not proceed to completion as they are reversible in nature. Some of the reactions are reversible in nature, so that it will not reach the equilibrium because they are reversible in nature. It can reverse at the end of reaction or in the mid of the reaction also it can be reversed. The extent to which a reversible reaction proceeds can be predicted by studying the principles of chemical equilibrium. How it will be reversed, how it will attain the equilibrium. To that, before proceeding the reaction, you have to know the principles of chemical equilibrium and principles of reaction which you are proceeding. Chemical equilibrium deals with the study of the significance of equilibrium constant and factors influencing the equilibrium constant. Here, completely you will study under how reactions are attaining equilibrium, and what is equilibrium constant and what are the factors influencing the equilibrium constant. There are two kinds of equilibrium, that is mainly physical equilibrium and chemical equilibrium. We will discuss first what is physical equilibrium, how it will be explained. There are different types of physical equilibrium. They are liquid vapor and solid vapor and solid liquid equilibrium is also present. First we will see liquid vapor equilibrium. When a liquid evaporates in a closed container, the molecules with relatively higher kinetic energy escape from the liquid surface and enter the vapor phase. When in the closed container, the liquid starts evaporating, means from the phase of liquid it will jump to the phase of gas. This process is called evaporation. The molecules in the vapor phase strike the liquid surface and enters the liquid phase. This process is called condensation, means when the liquid is converting to vapor, that is evaporation. When vapor is getting converted into liquid, when the molecules collision will start, it will convert it into liquid, that form we will call it as condensation. The collision of a molecules in the vapor phase with the liquid surface result in the exertion of certain pressure called vapor pressure of the liquid. What they are telling? The collision of molecules in the vapor phase with the liquid surface. Obviously in the mid of the region, the collision between molecules which are present in liquid phase as well as in the vapor phase, it starts get colliding. Their pressure will exert, that pressure will call it as vapor pressure of the liquid. The amount of vapor on the liquid is a constant because the number of molecules leaving the liquid phase is equal to the number of molecules entering the liquid phase from the vapor. Here the amount of both the phases means what all the molecules leaving the liquid phase and entering the vapor phase, and what are the molecules entering the liquid phase and leaving the vapor phase are both same and equal. At this stage, the liquid and vapor phases are said to have attained equilibrium. At this stage, when the molecules are equal in both the phases, that state will call it as the reaction has been entered to equilibrium. At equilibrium, the rate of evaporation is equal to the rate of condensation. We know now what is evaporation, what is condensation. Now, at the equilibrium, the rate of both evaporation and condensation is equal. It is represented by from liquid phase to gaseous phase, and from gaseous phase to liquid phase is same. This is equilibrium arrow mark. The double half arrows indicate that evaporation and condensation are taking place simultaneously. When liquid is in equilibrium with its vapors, the vapor pressure of the liquid remains constant. We have told about the vapor pressure also. This is also showing here. Next, solid vapor equilibrium. How that solid will directly move to vapor without the changing to liquid, like naphthalene, camphor, like that. Certain solids gradually go to the vapor phase without passing through the liquid phase. As I told, direct from solid to vapor it will form. It will not reach the liquid phase in between. This process is called sublimation. Example, naphthalene, camphor, iodine, etc. Suppose a certain amount of iodine is placed in a closed vessel. After some time, the vessel gets filled with violet vapors of iodine due to the sublimation. The intensity of the color gradually increases and becomes constant after some time. From colorless to it is getting colored means gradually it will increase, after some time it will be equal. That time we will call it as it has been reached equilibrium. At this stage, equilibrium is attained between solid iodine and iodine vapors. See here, iodine solid getting sublimized, that sublimation is taking place into iodine vapor. It can be reversed through the process called condensation. Next, solid liquid equilibrium. In solid liquid equilibrium, the solid and liquid phases coexist at the melting point of the solid under 1 atmospheric pressure. When any solid we have taken starts melting that or start converting that into liquid, when the first point it starts melting, right, that melting stage will call it as melting point. It will exist at the same time. If there is no exchange of heat with the surroundings, the mass of two phases remains constant. If there is no exchange of heat between system and surrounding, so the phases will remains constant. See, solid, this is in the ice phase, it is converting into liquid. Next, solid or gas liquid equilibrium. They are of two types, solids in liquids and gases in liquids. First we will see solids in liquids. When sugar is dissolved in water, a solution is formed. Suppose a solute is dissolved in a given amount of solvent such that no further dissolution takes place. Means we have taken some amount of sugar, we have taken certain amount of solvent like water. If it has been completely soluble in that given water, in that same water no further dissolution will takes place. To enhance the dissolution, you have to add more solvent. So that only they are telling. So then such a solution is called saturated solution. In a saturated solution, a dynamic equilibrium exists between solute molecules and those in the solution. Sugar in the solid, dissolution, sugar solution will form. If you get crystallized, crystallization process have been taken place means it will become again solid sugar. At equilibrium, the rate of dissolution of the solute is equal to the rate of crystallization, and the concentration of solution remains constant at a given temperature. Here, what all the two phases we are seeing, when both the phases are in same or equal, that time the reaction has been reached equilibrium. Next, gases in liquids. Carbon dioxide dissolves in water to give a solution. In the solution, a dynamic equilibrium exists between CO2 molecules in the gaseous state and the molecule dissolved in water. CO2 dissolving in water. At equilibrium, the mass of the dissolved gas in a given mass of water at a given temperature is proportional to the pressure of the gas above the solution. Here, gas is immersing in liquid, so the pressure of gas will be equal to the concentration of liquid. CO2 gas, it is in solution. Next, see here, the overall all aspects what we have discussed now. Liquid to vapor, here water, liquid, water to gas. So here pressure of water constant at given temperature. Solid to liquid, melting point is fixed at constant temperature. Solute and solute solution, concentration of solute in solution is constant at a given temperature. Gas in aqueous solution, gas in aqueous solution to gas is constant at given temperature. This is an example. Okay, these are the what all processes we have seen now and what are the conclusion we got. Next, general characteristics of physical equilibrium. By seeing the types of physical equilibrium, what are the general points we have understood? A physical process attains equilibrium only in a closed container at a given temperature. What all the physical equilibrium we have seen, that all takes place in closed container at a given temperature. Both the opposing processes occur at the same rate at equilibrium and hence the equilibrium is dynamic. There in the closed container, opposing two forces will be there. In example, liquid is converting into vapor means liquid is also one force, vapor is also exerting one force. Between two forces, the reaction has to reach the equilibrium. So, the equilibrium is a dynamic. Physical equilibrium is characterized by constant value of any one the parameters such as pressure, concentration, melting point at a given temperature. This physical equilibrium will be characterized by constant value when the pressure or concentration or melting point at a given temperature. The magnitude of such properties indicates the extent to which the process has taken place before attaining equilibrium. The magnitude of such property will indicate it before reaching the equilibrium. After reaching the equilibrium, it will be in constant. These are the 4 points or 4 general characteristics of physical equilibrium. Next, we will move on to chemical equilibrium. There are many systems where two opposing reactions occur together. It is called chemical equilibrium, where two opposing reactions are taking place. Next, reversible reaction. A reaction in which the products are converted back into the reactants is called reversible reactions. After formation of product, it will get reversed to the reactant. That reaction will be called it as reversible reaction. Or a reaction in which the reactants and products are interconvertible is called also reversible reaction. But in a reversible reaction, two reactions occur simultaneously. They are forward reaction in which the reactants are converted to products, backward reaction in which the products are converted back into the reactants. There is a reversible reaction, we understood now. It can be product to reactant, reactant to product. It can take place anything. But in a reversible reaction, two reactions should act simultaneously. What are those reactions? One forward reaction and another one backward reaction. Forward is reactant to product, backward is product to reactant, but it should act simultaneously. A reversible reaction is represented by writing arrows in both directions as shown below. This is a reversible reaction, arrow mark. Here H2 plus I2 is getting to form 2HI. It can be reversed into hydrogen and iodine. Conditions for the reversibility of a reaction. What are the conditions to get a reaction should reversible? Reaction must be carried out in a closed container. If it is in a closed container, it can be reversed. Both reactants and product must be present in a reaction system. Reactants and product should be in the reaction system. Required condition of the temperature and pressure must be maintained. Some temperature, whatever they have provided for to formation of product, same temperature and pressure should be maintained in the closed container. If not, it cannot be reversed if it is escaped from the closed container. So consider a reversible reaction A plus B giving rise to C, D. This is the overall graph, concentration versus time. Okay. This is A or B in the reactant side and C or D. It is reaching the equilibrium. What it is showing? In the initial stages, concentration of the reactants is higher and that of products is lower. In this, reactants is higher, products are lower. Hence, the rate of forward reaction is higher than that of the backward reaction. That time, when reactants are in higher concentration means forward reaction is higher than backward reaction. However, with time, the concentration of the reactant decreases and that of the product increases. Because reactants will be used to form the product, that time the concentration of reactant will decrease, the concentration of product will increase regarding to time. Hence, the rate of forward reaction decreased and that of backward reaction increases. After a certain time interval, the two rates become equal. Sometime, first in the reactant phase it will be more, in the product phase it will be less. After that, after the formation of product, the product phase will be more, in the reactant phase will be less. After the complete reaction has been taken place, the both phases will be equal. At this stage, the reaction is said to have attained equilibrium when the both phases, that is forward reaction and backward reaction, are having the same rate and both are having in the same phase, will consider as the reaction has reached the equilibrium. A reversible chemical reaction proceeds towards a dynamic equilibrium as time passes. By this, we can tell it is a dynamic reaction. In the equilibrium state, the reactants as well as products are present but have no further tendency to undergo a net change. Both are present but there is no tendency or there is no capacity to undergo a net change. Overall changes will not take place. In some cases at equilibrium, the concentration of products could be high in comparison with that of unchanged reaction. In some of the reactants, these are all exceptional case, in some of the reactants at equilibrium, the concentration of products could be high comparison with the unchanged reaction. Sometimes it is. In such a case, the reaction is said to be almost complete. In many cases, the equilibrium mixture has comparable concentration of reactants and products. Some examples for equilibrium system: nitrogen and hydrogen, it will form ammonia, it can be reversed. Sulfur dioxide and oxygen, sulfur trioxide will form nitrogen and oxygen, nitrogen oxide will form PCl5 will form PCl3 and Cl2. 2Hi, hydrogen iodide will form hydrogen and iodine. These are the examples of equilibrium states. These are the kilocalories which required for the proceeding the reaction. Next, characteristics of chemical equilibrium. Chemical equilibrium is a stage in a reversible reaction where the rate of forward and backward reaction are equal. Here we have understood that the rate of forward reaction and the rate of backward reaction should be equal to attain equilibrium. At equilibrium, the concentration of the reactants and products remain constant as long as temperature is maintained constant. At equilibrium, the concentration of the reactant and product will be constant till the temperature has been changed. Chemical equilibrium can be attained either from forward direction or from backward direction. There is no rule like the chemical equilibrium should attain from forward direction only or backward direction only. It can attain from any direction, but it should attain. At equilibrium, the concentration of the reactants and products remain constant though the reaction is in progress. This is because the two opposite reactions occur simultaneously at the same rate. At equilibrium, the concentration of the reactant and product remain constant though the reaction is in progress. When the reaction is in carrying out, that time only at equilibrium, the concentration of reactant and product may be constant. This is because the two opposite forces are reacting equally or simultaneously. Every substance is formed at the same rate at which it is consumed. Such equilibrium is called dynamic equilibrium. Means every substance is formed at the same rate. What all the substance is formed at the same rate and which it is consumed, that stage will call it as dynamic equilibrium. Thus a chemical equilibrium is always a dynamic in nature. Whatever has been formed, that will be that much of reactants will be consumed. The presence of catalyst does not affect the position of equilibrium, but in the presence of catalyst, equilibrium is attained quickly. The presence of catalyst, if any catalyst has been used in the reaction, it will not affect the position of equilibrium, but it will make the reaction to attain quickly the equilibrium, that's all. It will not affect with position of equilibrium. The dynamic nature of chemical equilibrium can be studied by using example of synthesis of ammonia by Haber's process. By giving a known process only, they are explaining about the nature of chemical process. That is synthesis of ammonia by Haber's process. That is nitrogen and hydrogen will form ammonia. Haber started with known amount of dinitrogen and dihydrogen maintained at high temperature and pressure and determined the amount of ammonia present at regular intervals. He found that after some time the composition of mixture remains the same, which indicated that the reaction has reached equilibrium. Means Haber started with known amount of dinitrogen and dihydrogen, so maintained at high temperature and pressure. It was the experimental setup. Okay. He found that after some time the composition of mixture remains same. After some time the composition of what all the mixtures he has been used, that approach same. Means it has been reached equilibrium. See here, dinitrogen and dihydrogen has been used. This is molar concentration, this is time. After some time ammonia has been formed. The synthesis of ammonia is carried out with exactly the same conditions using D2 to understand dynamic nature, that is dihydrogen. This reaction mixture reached equilibrium with same composition when H2 was taken. Okay. After equilibrium is attained, those two mixtures are mixed together and left a while. They are taking the dihydrogen and they are taking the dihydrogen and the reaction has been started. When the equilibrium has been attained, the two mixtures are mixed well. When the mixture at equilibrium is analyzed by mass spectrometer, it is found that the mixture contains ammonia, NHD2, ND3, H2, HD and D2 was found. Means it was mixing properly. This indicates that equilibrium forward and backward reactions continues. Thus, chemical reactions reach a state of dynamic equilibrium in which the rate of forward and backward reactions are equal and there is no net change in composition. So, this point is overall very much important, because by understanding this experiment, by understanding the general characteristics of chemical equilibrium, the chemical equilibrium or chemical reactions reach a state of dynamic equilibrium in which the rate of forward reaction and the rate of backward reaction is equal and there is no net change in composition. This is about the chemical equilibrium. Equilibrium can be attained from both the sides. Consider the following reaction: hydrogen and iodine, hydrogen iodide will form. This is another example. If we start the reaction with equal concentration of hydrogen and iodine, reaction proceeds in forward direction, attains the equilibrium. When the reaction is started by taking hydrogen iodide alone, backward reaction occurs and equilibrium is attained. It is observed that in both the cases at equilibrium, the total number of hydrogen and iodine atoms are same in a given volume. The same equilibrium mixtures is obtained whether we start it from pure reactants or pure product. It will attain back. See here, concentration, this is time. Here hydrogen and iodide, iodine they are using. Here the formation of hydrogen iodide will form. After equilibrium, see, it can be reversed. into hydrogen and iodine, here also it will increase. This is about the characteristics of chemical equilibrium. We have understood that physical equilibrium, what are physical equilibrium and how it will be explained, and what is chemical equilibrium with so many examples. In the next session, we will discuss about rate or velocity of a reaction, law of mass action, law of chemical equilibrium and equilibrium constant. I hope you have understood completely whatever I have taught today. So, we will meet in the next session. Thank you.